Every day, the world's computing needs expand as AI, machine learning, and cloud infrastructure push new boundaries. In order to meet those needs, data centers with complex network infrastructure are being built at an expanding pace. Active optic cables, or AOCs, are used to connect these servers and networking equipment. Currently, these cables are deployed by hand in cable trays, which are mounted 10 feet above the ground. The technicians who install the cables must stand on ladders to reach these heights and move the cables, which can be very dangerous. Typically, 3 to 5 technicians are necessary to install the AOCs, and the task is very time-consuming. Our project aims to improve the safety for operators by reducing both the number of ladder climbs necessary to deploy the AOCs and the number of technicians needed to install the cables, which enhances the deployment process. Rather than physically dragging the cables by hand along a 40-foot section of cable trays, we designed a system that requires only 2 technicians to operate and reduce the deployment time from 5 minutes to 2 minutes. During the design process, meeting Microsoft's requirements was our top priority. Key factors that influenced our decisions included the need to keep the prototype cost under $500, the speed at which the cables were to be deployed, safety standards, and the durability required for drop tests. Additionally, we prioritized using interchangeable parts for easy replacement if a component were to fail.
Our system was composed of 3 different sub-assemblies: the cable tray mounting, which connected our system to the cable trays, the cable interface, which protected the AOC cables and the transceiver ends, and the cable tray deployment system, which consisted of a winch and pulley and allowed our system to move cables along the length of the cable tray. While we did use some off-the-shelf components, including rope, mounting hardware, and Velcro, we are proud that almost all of the system was completely custom designed by the team. In total, we created 29 new components in SolidWorks. We selected SolidWorks since the team had a fair amount of experience with that software. By creating so many custom parts, we're able to best meet our system requirements in the most efficient and effective way possible. We created a custom mounting design that allowed our system to interface with both 12 and 24-inch cable trays, the 2 sizes that were most commonly used in Microsoft data centers. The cable tray mounting supported a rail, which allowed our cables to be deployed along the lateral widths of the cable tray. The rail in turn supported a winch mount bracket, which supported this spool and pulley.
In order to couple the active optical cables to the deployment system, we invented a cable interface which we nicknamed the cable boat. It is capable of accommodating up to 16 transceivers at a time, which is the maximum bundle size used in Microsoft data centers. The cable boat offers 360-degree protection of the active optical cable transceivers during deployment. Its use of Velcro straps makes loading and unloading cables easy and time efficient. A carabiner clip connects the cable boat to the rope of the deployment system. On the end of the cable interface is a magnetic safety mechanism. If the pull force of the deployment system exceeds a certain threshold, the magnetic attachment will automatically disconnect itself, preventing the possibility of cable damage from excessive tension.
The final prototype was made from a mix of aluminum, steel, or Bruden-printed plastic parts, based on the expected load case in 3 series parts. We relied on a local laser cuttle company, TMN, to cut some of the harder sheet metal parts, and the AME shop to do some of the CNC parts. This allowed the team to expedite the build process in the shop and gave us time to do the minimum manufacturing for all the other. We used lathes, bandsaws, grinders, and mills to make our metal cars in-house, and kept a 3D printer running during this time so we could have 3D printed parts coming out raw. Over the course of the project, we experienced a number of challenges that demanded creativity and engineering. In making our MVP-1 prototype, we experienced problems with our 3D printer's extruding tip and heating element. This issue set us back a few days while we fixed it. In manufacturing, we had a couple of simple mistakes that required remaking of the part. On the one hand, this allowed team members to develop better machining skills, but we also risked having to purchase more inventory. Regarding procurement, we had a setback with our cable trays as they got lost in transportation on their way to the U of A. This forced us to create a 3D printed cable tray portion in order to continue with our testing and stay on schedule. But with all the setbacks we were able to learn from that, we continued to move forward to filter our error.
We created our first functional prototype back in October for our MVP-1 test. It consisted of all 3D printed parts on 3D printed cable tray mock-ups, since the actual cable trays were still in transit and hadn't yet been delivered. The prototype was simple, it was cheap, and it wound up costing under $50, but it allowed us to be confident in our initial deployment concept moving into MVP2 and CDR. Our final prototype was made from a mix of aluminum, steel, and 3D printed plastic parts, based on the expected load case for each.
In order to satisfy our system requirements and ensure that our design ideas would work before building them, we conducted a series of different analyses. One of the analyses we performed was a series of force and torque studies in SOLIDWORKS and MATLAB. We designed the system to have a minimum factor of safety of at least 1.25 for all parts. After conducting our analysis, we found that we had exceeded our initial goal, with our design having a minimum factor of safety of 1.34.
Through advanced planning, risk management, and successful prototyping, we were able to create a product that finished ahead of schedule, under budget, and met all of the system requirements laid out by Microsoft. This product will help Microsoft data centers to run more efficiently by improving safety and decreasing the amount of time required to deploy cables along the lanes of their cable trays.
Thank you for watching. Our goal is to create a safer, more efficient cable deployment system for Microsoft data centers, and we have successfully achieved that.